So, good morning. Still waiting for a few more seconds. People are just arriving. So, good morning. Dear colleagues and friends, it's a great pleasure to be here. It's a great pleasure to see you all in real life, in 3 dimensions, well and healthy. It's also a great honor to chair this plenary session of Professor Jacqueline O'Connor. I do not need to introduce Jackie to you. However, it seems appropriate to still spend a few words about her track record and her background. Jackie is a professor of mechanical engineering at Pennsylvania State University, and she's the director of the Center for Gas Turbine Research, Education, and Outreach. Her laboratory focuses on unsteady combustion, on fluid mechanical phenomena, and instability, so in other words, on thermoacoustics. Jackie holds a bachelor's in aeronautics from MIT, and then did a master's and PhD at Georgia Tech and the group of Tim Lewin. This, she told me, was however not her first encounter with thermoacoustics. That actually was at college level already, quite early if you ask me. She afterwards went for a postdoctorate at Sandia National Labs, where she worked for 2 years on diesel fuels, diesel engine combustion, and fluid mechanics and instabilities in this type of machine, before returning into academia in 2013, joining Pennsylvania State as faculty. Jackie is a fellow of the ASME, she's an associate fellow of the AIAA, and now she's here. She's going to talk about the role of fluid dynamics in thermoacoustic combustion instability. Ladies and gentlemen, please join me in welcoming Professor Jacqueline O'Connor.
All right, thank you all very much, and thank you so much to Andreas for that excellent introduction. A few other words of thanks as I get started. First, I'd like to thank Benedict and Niels for inviting me to give this talk. It's a real honor. And I also have a lot of people to thank, both students and collaborators that I've worked with in the area of thermoacoustics, students on the left, collaborators on the right. The folks whose names are underlined are folks whose work you're going to see as part of this presentation today. I do want to acknowledge one particular collaborator, and that's Dr. Santosh Hemchandra. He's an associate professor of aerospace engineering at the Indian Institute of Science in Bangalore. He's my academic sibling. We've worked together since we were in grad school at Georgia Tech, and a lot of the ideas that I'm going to talk about, particularly towards the end of the presentation, are ones that he and I have developed together. Also, research doesn't happen without funding, and I've been really fortunate to receive funding from the US Department of Energy and the National Science Foundation in the area of thermoacoustics. I'm also very fortunate to work with a number of industry sponsors, particularly Solar Turbines and GE Research. And then also, I want to thank my home Department of Mechanical Engineering at Penn State. All right, so this talk today is on thermoacoustic instability, but if you're familiar with the field of thermoacoustic instability, it's a lot of fun, because it's a lot of interdisciplinary work. And so it requires not just a deep knowledge of combustion fundamentals, but also fluid mechanics, acoustics, nonlinear dynamics, dynamical systems theory, and a number of other different topics. And so if you look across the community, many of my peers in thermoacoustics are here today, we all take different sort of lenses in which we look at this problem. And so if you enjoy this talk today, I highly encourage you to talk to the many other folks here this week who work in thermoacoustics to learn more about their particular angle at looking at the problem. But the way that we're going to look at it today is through the lens of flow dynamics and the overlap between thermoacoustic instability and hydrodynamic instability, or the inherent instabilities in flow fields. I recognize, however, that many of the topics that are necessary for understanding thermoacoustics problems, acoustics, fluid mechanics, nonlinear dynamics, may not be part of the typical daily regimen for many in the combustion community. And so my goal today is to give an overview of the problem, provide enough background so that you can understand some of the fundamental challenges. I'm also particularly interested in speaking today to the graduate students in the audience who are getting really good educations in the fundamentals of combustion and who may be looking for interesting problems to work on in their careers. This is one of the most interesting and fun problems to work on, and so hopefully I can convince you of that today. So like any good professor, I wrote my learning objectives for this talk, and there are 4 things that I'd like you to take away from this lecture today. The first is that thermoacoustic instability is a critical issue for a wide range of technologies, but there's no one way to solve the problem. It's a highly geometry-dependent problem. It has really non-monotonic behaviors and a lot of nonlinear behaviors that make it a challenge to solve. I tend to call this job security, but you can also look at this as being just an interesting problem. Second, the focus of today's talk is on the intersection of fluid mechanics and thermoacoustic instability. And one of the things that I really want you to take away from this is that all the flow features that we use to promote flame stability and high performance, low emissions technologies are the same ones that drive hydrodynamic instability. And so you get the benefit of good flame holding, but you introduce all these other challenges. So these thermoacoustic and hydrodynamic instabilities couple in really interesting ways, but one of the things that I'm going to argue in the second half of the talk is that we can actually sort of utilize the hydrodynamic instability characteristics of the flow field to suppress thermoacoustics. And finally, this is a problem that obviously requires deep knowledge of fundamentals, but it also requires a knowledge of the technologies in which these instabilities occur. Thermoacoustics doesn't show up in the wild. It shows up in engines and devices that we have designed. And so knowledge of both the fundamentals and the application is really important. That said, one of the other things I'll argue towards the end of the talk is that pretty basic theory that's computationally tractable has a real potential to reduce the likelihood of instabilities all the way in the design phase. All right. So let's get started. So where does thermoacoustic instability occur? Basically, you can get thermoacoustic instability anytime you put a flame in a box. And as combustion engineers, that's what we tend to do, is put flames in chambers. And so this has the potential to occur pretty much anytime. So some examples of where we see thermoacoustic instability, probably the most famously is in rocket engines. This is the F1 rocket engine. 5 of these were placed on the bottom of the Saturn V rocket that took us to the moon. And it has some famously intense instabilities. Much of the work in thermoacoustics today focuses on low emissions gas turbines. All the tricks that we played to reduce the emissions, particularly the NOx from these engines, made them highly susceptible to thermoacoustic instability. And if you look across the modern literature, it's these 2 technologies that you'll see a lot of work focused on. However, thermoacoustic shows up in a lot of different places. And one really interesting place is in big industrial systems, air heaters, package boilers, furnaces. Because these are really high heat rate devices, they can have really intense instabilities. But because they're so large, they tend to be really low frequency, on the order of tens of hertz. And finally, you don't have to go to large industrial exotic technologies to find a thermoacoustic instability. You could just look in your basement. You can, in fact, get instabilities in gas-fired water heaters. So all the way from the lowly water heater to the mighty F1 engine, we have the potential for thermoacoustic instability, and a lot of the fundamentals that drive these instabilities are the same in this range of technologies. So let's quickly talk about those fundamentals, and I have to give a lot of credit to yesterday's speaker for setting me up so well on this. But thermoacoustic instability is driven by a feedback between the heat release rate oscillations from the flame and acoustic oscillations inside the combustor, which include both oscillations in pressure and acoustic velocity. So let's break these down into their constituent pieces. First, we'll talk about acoustic modes, knowing that many here may not be too familiar with acoustics. I'm going to assume that a combustor is a cylinder. Many of them are. Just as an example here, and is a 3-dimensional object, you can get 3 components of an acoustic mode shape inside that device. The first is the longitudinal mode, so I'm looking sort of on the side of this combustor, let's say flows going from bottom to top, and I can get a resonant harmonic oscillation inside that combustor, fluctuations in both acoustic pressure and acoustic velocity as a result, where the fluctuations in both pressure and velocity oscillate in the direction of flow. And those are referred to as longitudinal modes. If I turn that combustor on its end, I can also get fluctuations in the acoustic properties as a function of radius. We refer to these as radial modes. You can think of like hitting the top of a drum and the oscillations that emanate from there. And then finally, you have azimuthal modes. And so now you have pressure and velocity fluctuations in the theta direction. And azimuthal modes are particularly interesting because they can both be standing, like what I've shown here, or they can be spinning. And there are some interesting issues that arise when you have either one of those, which I'll talk about later. The other part of this feedback loop is that flames are actually really sensitive to incoming perturbations. And so the movie that I'm going to show here is from Daniel Durock's EM2C. Here, this is just a laminar Bunsen flame, a high-speed Schlieren video. He's got a speaker at the bottom of the tube and is exciting the flame at 50 hertz. And what you can see is the very large wrinkles on the flame that are excited by the oscillations upstream of the flame that cause significant flame response and, as a result, heat release rate oscillations. And so now to close the feedback loop, we have acoustic oscillations that can resonate inside the combustor. You have heat release rate oscillations from this highly sensitive flame. And if you think about heat release rate oscillations, this is a periodic expansion and contraction of the gas. This is just compression expansion work, or PDV work, that the flame does on the surrounding fluid. And this work can transfer energy from the flame into the acoustic mode, closing the feedback cycle, such that if all of this is happening relatively in phase, you can get a feedback and an instability. Typically, however, there's more going on. And in between the acoustics and the flame heat release rate oscillations is something referred to as a coupling mechanism. In the paper that accompanies this talk, I talk about a whole bunch of different coupling mechanisms. But in this talk, I'm only going to focus on one, which is velocity coupling, or the excitation of the flow field by acoustics that then leads to the flame heat release rate oscillations. We've known for quite some time that fluid mechanic coupling is really important for thermoacoustic oscillation. This is a picture from a classic study by Rogers and Marble that was published in 1956. This is a bluff body stabilized flame where flows going from left to right. That triangle is the bluff body that the flame is stabilized inside a relatively thin channel. And you can see from this Schlieren photograph that the flame is stabilized in the separating shear layer off the back of that bluff body. They could operate this combustor in an unstable mode. And so this is what it looks like when it's unstable. They referred to this as screeching combustion. We still today refer to this as a screech mode. It's a really great word. And so what you can see from this Schlieren photograph is that there are large fluctuations on the flame that are causing these heat release rate oscillations. Although this isn't a direct velocity measurement, it doesn't take too much creativity to infer that these large oscillations on the flame are coming from vortices that roll up in the separating shear layers that are excited by the acoustics. And so in order to understand these fluid mechanic coupling mechanisms, we have to think a bit about what the flow field looks like inside a combustor. But combustors look very different for different applications. So here are a number of different examples from authors in the community of really different flow fields. But if you look across combustor technologies and sort of do your eigenvector decomposition of what flow fields look like, there are really two basic flow features that we use to stabilize flames in combustors. And they are shear and recirculation. So the top picture here is from a classic study by Brown and Roshko of a mixing layer. You have a high velocity on the top and a low velocity on the bottom, and you create this nice region of shear in the middle. On the bottom is a very low Reynolds number example of recirculation zones on both a forward and backward facing step. But these are the types of features that create low velocity zones that allow for flames with flame speeds, as we know, are not particularly high compared to the flow velocities through these devices. And so these regions create low velocity regions where the flame can stabilize. We sort of use two canonical flow fields in order to create regions of shear and recirculation. The first one are wake flows. So on the left, I'm showing a picture from Prasad and Williamson. This is a study of flow over a cylindrical bluff body where flows going from left to right. You can see the recirculation zone behind the bluff body and the separating shear layer as the boundary layer separates off the bluff body, these regions of shear. Again, region of low velocity, good mixing, great for flame stabilization. The other flow field that we use to promote flame stabilization are swirling flows. So on the right is a study from Bianchomaz and Her, where you have in each of the four pictures, again, flow going from left to right. This is a swirling jet at a high enough level of swirl to create a process called vortex breakdown. So vortex breakdown is where the flow kind of collapses in on itself in the center line. You get this big recirculation zone. And so you have a nice region of shear and recirculation along the center of the flow that promotes flame stabilization. So if we look at actual combustor technologies, you can see these features built in, sort of layered on top of each other. So on the left, I'm showing a cross-section of a GE F-class engine, which is a very common heavy frame engine configuration for power generation. Flows coming in from the compressor, you can see that arrow where it says compressor air. The flow does a 180 around the outside of the combustor liner. It does another 180 into the injector where it mixes with fuel. It burns in the combustion zone, and then the hot products are sent through what's called a transition piece into the first stage turbine nozzle. But if you look at those injectors, which I've shown pictures on the right, the top picture is the injector without its outer sheath, and the bottom picture is with the sheath on, you can see a lot of features that promote these two different flow fields. So first, we have swirling vanes, so they add swirl to the flow to create vortex breakdown. There are those posts in the center of the injectors. We refer to those as center bodies. Those basically create big wake regions behind them. And then if you look at that cross-section of the engine, you can see a lot of regions of sharp area expansion. In the biz, we refer to these as dumps. And this promotes more recirculation. So you have all these different regions that are promoting shear and recirculation that keeps the flame in the combustion zone at these really lean mixtures where we're not producing that much NOx, and is good for flame static stability. The issue is that if you really looked at these pictures before, you'd notice that yes, we have a lot of regions of shear and recirculation, and that's great for static flame stabilization, but at the same time, it's exactly the actions of shear and recirculation that tend to promote hydrodynamic instability in these flow fields. And so if we look at the wake picture at the left, you can see in these separating shear layers small vortices that form in the shear layers. Downstream of that, you can see large vortices that form in the wake. These vortices are manifestations of the hydrodynamic instability present in the flow field. You can similarly see this in the swirling flow in the shear layers between the recirculation zone and the annular jet. Really nice roll up in those shear layers. So now I'm going to take a quick break and talk about hydrodynamic instability and give folks a little bit of a background, recognizing that this might not be something that folks are very familiar with, and talk about when a flow is unstable. So an unstable flow is one where an infinitesimally small disturbance to the flow will grow and propagate with the flow. And actually, I think to start talking about unstable flows, it first helps to talk about stable flows. And we're going to use some excellent PowerPoint art to make this point. So a stable flow is one that has a disturbance, or when disturbed, it damps out the disturbance. So if I come upon a stable flow and I kick it, I will see some response, right? And so the flow oscillates because I've kicked it, but then as that disturbance convects downstream, the oscillations are damped out, both in space as it moves downstream and in time, such that if I came back to the flow a minute later, I wouldn't see any other oscillations. So this is a stable flow. There are two types of unstable flows, and I'm going to give this explanation from a very high level. Again, I would point you to the paper for a much more subtle discussion of flow instability, but they generally fall into two categories. The first category are disturbance amplifiers. So some flows, if I kick them, actually amplify the disturbance. And so after I poke the flow, I see an oscillation, and if I watch that oscillation as it convected downstream, it would oscillate, typically harmonically, and it would grow in space. However, flows that are disturbance amplifiers don't keep it going, and so if I came back a minute later, I wouldn't see any more oscillations because that disturbance convected away with the flow. There are, however, a class of flows that are self-excited. We call these globally unstable flows. And so if I came upon a globally unstable flow, it would already be oscillating. And so if I looked at it in space, like I have in this picture, I can see oscillations, again, typically harmonic. Tried to make them harmonic in PowerPoint. Harmonic oscillations that grow in space. And if I stood at one location in space and looked at the oscillations in time, I would see harmonic oscillations in time. You may ask yourself at this juncture, and it's the right question to ask, what happens when I come upon my globally unstable flow and then I punch it? And the answer is it's not entirely clear, and we're going to talk about this at the end of the presentation. Also, emojis are what happens when you ask a millennial to give a plenary lecture. All right, so let's look at what this actually looks like in actual flow fields instead of my terrible PowerPoint art. So we're going to go back to this mixing layer from Brown and Roshko. And so again, high velocity on top, low velocity on bottom. And you can see there's nice turbulent oscillations in this mixing layer, which was what we wanted for flame stabilization. But this is a type of flow that's a disturbance amplifier. So the initial disturbance isn't a punch. In this case, it's the small level of turbulence in the boundary layer on the splitter plate before it separates off this shear layer. And because this is a linearly unstable flow, you can get amplifications of those even very small disturbances. The disturbances manifest as these coherent structures in the flow field. So you see these nice coherent vortices in the shear layer. And one thing that I want you to know is that they have a particular wavelength, and one of the things I'll talk about later is this wavelength's actually pretty predictable. Globally unstable flows, a good example, actually one of my favorite examples, is the flow behind a wake. So this is a video that shows a wake flow at a Reynolds number of 200. At the beginning of the simulation, you had a perfectly quiescent flow heading to this bluff body from left to right. But because this is a self-excited oscillator, it's globally unstable, you get this absolutely gorgeous asymmetric vortex roll-up in the wake, which is referred to as the Bernard von Karman vortex streak. This instability arises at Reynolds numbers as low as 47, so you really don't need that much, you don't need any, really, theoretically, incoming perturbation in order to get this instability to occur because this flow is self-excited. So now if we go back to our two combustor flows, right, we use wakes and we use swirling flows in order to help stabilize flames. Each of those two combustor flows has their own global instability. So the first one is this wake instability or von Karman vortex streak. So this video is from my colleague Ben Emerson at Georgia Tech. This is a bluff body stabilized flame, and every once in a while you'll see a really nice asymmetric oscillation in the wake, and I'll talk about why it's only happening every once in a while later in the presentation. The other one in swirling flows is referred to as the precessing vortex core. So the precessing vortex core is what happens when that vortex breakdown region in the middle of the flow precesses around the center line, and you get this massive oscillator that forces the flow in a helical motion. And so this is a high-speed particle image velocimetry video that was taken by an undergrad in my lab, Mark Frederick, who is here this week as a graduate student. And so we have seeding particles, the laser coming through, and you can see the pretty violent oscillation of the shear layers as they respond to this precessing vortex core in the center. So that was just talking about non-reacting flows, but you can get some really interesting behavior when you add a flame. So the presence of a flame can significantly impact the behavior, particularly of globally unstable flows. And so to show this, I want to highlight a study from Rob Erickson and Marius Sotiriou, where they looked at a wake flow and a flame stabilized in the wake flow. So on the left side of this figure is instantaneous vorticity. On the right, The top is time average vorticity, the bottom is time average temperature. And we're going to start at the lowest picture. What they did basically was they changed the temperature ratio across the flame, so burnt temperature over unburnt temperature. And as you can see, when that's equal to 1, or you have no flame, you get that really nice asymmetric von Karman vortex street, which is what we would expect. So then you add a flame, and at low temperature ratios, the black line, which is the flame, follows that oscillation really nicely. But as we start to crank up the heat release, so the temperature ratio across the flame, it actually suppresses the global instability. And you can predict this using theory, which we'll talk about later. You can also use a baroclinic torque argument and kind of right-hand rule it to show how the vorticity is being suppressed by the density gradient across the flame. So if we looked at this, again, in movie form, the parameter that actually matters is not the temperature ratio, it's the density ratio. So in Ben Emerson's work, again on the right, low density ratio, you get every once in a while that nice asymmetric vortex shedding. But if we have a low density wake or a higher heat release, we get absolutely no asymmetric motion. It's just a turbulent flame brush. And so the flame really can affect the global instability in the flow field. However, one of the things that's really interesting is where the flame sits in the flow field is really important. So going back to this work from Rob and Marios, what they did, because this was LES, they could change the turbulent flame speed and basically allow the flame to stabilize outside of the shear layers because it could propagate into faster and faster flows. So as you go from top to bottom, that turbulent flame speed's increasing, the flame moves out. And what ends up happening, you can see as the flame completely moves out of the shear layers, you get that asymmetric vortex shedding again. So the non-collocation of the shear and the density gradient changes the stability of the flow. For very different mechanistic reasons, but in a similar manner, this happens in swirling flows as well. So on the right is a picture from a study from Michael Storr's group at DLR in collaboration with Kilian Oberleithner's group at TU Munich, where they have this really cool experiment where the flame sort of intermittently changes from bluff body stabilized on the top to a lifted flame on the bottom. When the flame is stabilized on the bluff body, there's no global instability. When it's lifted, they get a precessing vortex core. And this kind of happens intermittently, as you can see in the time series on the bottom. If you're interested in this, I highly recommend reading this paper because they're able to show mechanistically how the flame and the precessing vortex core feed back on each other, such that the flame affects the precessing vortex core, and the precessing vortex core affects flame stabilization. So this is a two-way coupling behavior. Okay, cool. So quick break. What have we learned so far? Hopefully I've convinced you that thermoacoustic instability is important and that it shows up in a bunch of different technologies that we care about, but it's a challenging enough problem that it's something that we should continue to work on. And I hope I've also showed you that these flow features, shear and recirculation, that we use to stabilize flames can cause some really fun but challenging hydrodynamic instabilities in flows. So now for the remainder of the presentation, we're going to look at sort of the overlap of these two things. And we're going to look at how thermoacoustic instability interacts with flows that are disturbance amplifiers first, and then how the thermoacoustic instability interacts with flows that are globally unstable or self-excited oscillators. So let's start with the disturbance amplifiers, because these could be particularly problematic. Right? If I have a thermoacoustic instability and that's creating this very loud acoustic field in a combustor, that's a really good source of excitation, and if I had a disturbance amplifying flow, it would amplify those disturbances, and that's exactly what happens. So I think one of the best ways to show this is to start with flow off a backwards facing step. So this is an experiment at MIT, Ahmed Ghoniam's group. John Hong was the grad student who did this work. And on the top, you can see flow going from left to right over the step. And this is an instantaneous PIV image, so you can see, dense particle seeding in the reactants and not dense in the products, and the flame front is in between. On the bottom is the time average velocity field in those arrows, and then the vorticity field in color. And so they can run this combustor in a few different modes and get a few different instabilities, but One of the ones is a longitudinal instability with a very violent flame oscillation. So here I'm showing a video of the flame oscillation. As the flame is responding to the acoustics, it actually flashes back over the step and then gets rolled up. And you can see this really extreme oscillation in the flame responding to a longitudinal instability in the system. The system, I actually did some of my undergraduate research on this experiment way back in the way back. It's a very long combustor, and so the instability frequency is about between 40 and 60 hertz, depending on how you run it. So now if we look at what's happening in the flow field, this is a phase-averaged picture of the vorticity in color and a whole bunch of different flame edges at the same phase. And what we can see is as the acoustic velocity pushes forward, you get this nice shear layer roll-up off the step. The flame wraps around that vortex, and then as you get the pull part of the acoustic velocity, the flame pulls back and flashes back, and it does this repeatedly. So here, this shear layer is amplifying the acoustic disturbance that's coming from the thermoacoustics. You're getting really nice oscillations of the flame in response to that shear layer because the flame is stabilized in that shear layer, and you get this really violent response as a result. So this is a really classic example of coupling in a longitudinal situation, but one of the first things I told you was that we had all these different modes of acoustics inside combustors. And one of the most interesting ones are transverse or circumferential modes. So a lot of combustors, particularly in gas turbine technologies, are annular, like the one shown on the left. This is a simulation from Thierry Poinceau's group of a helicopter engine, which is an annulus. And so you can have longitudinal modes in these systems, but one of the common mode shapes is actually these azimuthal, or sometimes referred to as circumferential modes. So the images on the right are data from Nick Worth and James Dawson's group at NTNU, where they have an annular combustor with 12 swirling flows in it. And they're taking an image looking down onto the top of the annulus, and what they're plotting here are fluctuating chemiluminescence from the flame. And it takes them getting used to these images, but one of the things that you can see if you sort of watch it enough is that the image on the left is a standing wave, and so with its nodal lines sort of going at a 45-degree angle across. And so you see the fluctuations in the flame as a result of that oscillation. And then on the right is actually a spinning wave. And so they've indicated the direction of spin with the arrow, but again, if you watch it, you can kind of see the disturbance as it spins around the flame. And so you can imagine that depending, if you look, even if these aren't familiar to you, you look at two flames, they're not doing the same thing at the same time. In a longitudinal instability, they'd all be responding together, but because here the acoustics are oscillating transversely to the direction of flow, you get this variety in response from nozzle to nozzle. So actually in my PhD research, we were some of the first folks to look at this for gas turbine applications, and we looked at the two extremes where we had a symmetric forcing case, so the acoustic field was symmetric, you got a big pressure fluctuation over the nozzle, and then the asymmetric case where you have no pressure fluctuation in the center line, and it's it is out of phase on either side. And so if we look at the flame response to the symmetric forcing, big pressure fluctuation on top, you get a big symmetric oscillation as a result. But if you look at the asymmetric forcing case, the flame's kind of doing a shimmy back and forth as a result of the asymmetry in the acoustic field. And what's actually driving this response is the flow field. So now I've flipped the data, flow's going from left to right. If you look at the inner shear layer of these vorticity plots, you can see that in the center, in the symmetric case, the shear layer is responding symmetrically. And then in the asymmetric case, it's actually exciting a helical response in the shear layer. So not only are these disturbance amplifying flows sensitive to the frequency of forcing, but it's also really sensitive to the symmetry of forcing. And this can have some major implications for the global heat release rate oscillation. You get a finite global heat release rate oscillation from a symmetric forcing, but in many cases you can get no global heat release rate forcing response from the asymmetric case. So this flame can be violently shimmying around but there's no global heat release rate oscillation, which is important for that thermoacoustic feedback loop. So finally, the last thing I want to talk about in disturbance amplifiers is this concept of receptivity. You can imagine if we talk about, okay, if this flow field is amplifying a disturbance, how much is it amplifying? And we refer to that as the receptivity of the flow. And so I'm going to talk about this by telling a story. And this is a story that goes out to the graduate students and undergrads who may be a little bit frustrated with their PhD advisors right now. Because the student who did this work, who started this work, was an undergraduate honors student in my lab named Ben Matthews. And I gave Ben what I thought was a really simple task. I taught him how to do PIV, and I said, look, I want to measure the response of the shear layer to longitudinal acoustic excitation at a bunch of different swirl numbers, and we're going to see how it changes, and this is going to be great. There was a transfer function involved. It was going to be a lot of fun. So we have this experiment in my group where we can change the swirl number. So the number's on top of the swirl number, so that's the ratio of azimuthal velocity or azimuthal momentum to axial momentum. And so the first line of pictures is the time average axial velocity. So if you have no swirl, you just have a non-swirling jet. And as you increase the swirl, you can see the flow sort of bifurcates, and then you get that nice vortex breakdown bubble with increased strength of recirculation as you increase the swirl velocity. And then the low pictures are ones of the swirling plane. This data was taken by two undergrads later, Mark and Sean, where they, at the black line, cut the flow and looked at the swirling velocity. So as we increase the swirl number, you can increase the amount of swirl. So we chose two frequencies, 600 hertz and 1800 hertz, and we chose them because 600 hertz is the most amplified frequency in the non-swirling jet. So we knew we were going to get a nice response there. And so what I'm plotting here is the coherent vorticity response at the forcing frequency. So you do some Fourier transforms and pick out the component at the forcing frequency. And you can see in the non-swirling case, you're getting beautiful vorticity response in the shear layers, which is what we expected. So then Ben goes and he starts increasing the swirl number, and you can see as we increase the swirl number, that coherence goes away. I didn't even plot 1.43 because there's nothing there. And so Ben showed me this data, and I was like, I think you might be doing something wrong. And I made him retake it like 3 times because I didn't understand what was happening at the end. So poor Ben. He comes back after like week 3 and is like, Dr. O'Connor, I swear I'm doing this experiment correctly. Like the speakers are on. He had 2, we used police sirens as acoustic drivers. He had 2 police sirens turned up to like the maximum voltage on the waveform generator. And he showed me this pressure spectrum. And so this is from a pressure transducer that's right before the dump plane, right under the flow that we're looking at with the PIV. And he showed that big peak on the right at 1800 hertz. And he said, see, I promise, like the acoustics are on. Dr. Yetter's getting really mad at me because Rich Yetter's office is right across from this lab, and all he was hearing was 1800 hertz all day. And Ben was like, but there's this other really big peak in the spectrum, and I don't know what it is, but it doesn't look acoustic. So then we decomposed the flow at 2 different frequencies, and at the acoustic frequency, we saw nothing. But when we did the decomposition at that big peak, we saw this. And anybody who works in swirling flow fields knows exactly what this is. This is a precessing vortex core. And so what seemed to be happening was as we cranked up that swirl number, we were exciting the global instability in the flow field, and it was completely killing any response to the very high intensity acoustics that we were sending into the experiment. And so like any good experimentalist, I have a best friend who's a theoretician. So I went to Santosh Hemchandra at IASC and his student Kiran, and we said, can you help us explain this? Because I now believe that Ben's doing the experiment correctly, but we don't understand why this is happening. So what he did was what's called a linear hydrodynamic stability analysis. So here we decomposed the flow field, all flow parameters, Q, so any component of velocity or pressure or whatever. If the flow is statistically stationary, you can decompose it in what's called a triple decomposition. So you can say you have the time average, the phase average, or the coherent motion, and then the turbulent motion. And then you take the Navier-Stokes equations and you linearize them around that coherent motion, And basically, just like the PowerPoint art I was showing you before, we kick the Navier-Stokes equations and we look at how they respond for this particular flow field. So the driving function on the right is a delta function in space. So we kick it at a particular location, and we hit it with a harmonic oscillation at the forcing frequency that we've been using in the experiment. What we get is what's called the impulse response, and that term that's in the red box, the K plus, is the downstream spatial growth rate of that impulse at that given frequency, and we plot it as a function in this term. You can read more about why we do that in the paper below, but basically if this term is greater than 1, that means that the flow field is amplifying the disturbance. If it's less than 1, then it's damping the disturbance. So we go ahead and we kick the flow at each of these different locations and look at this term, and you could see for all the low swirl numbers where Ben was seeing a response, we were getting positive growth rates, but for those 2 highest swirl numbers where the precessing vortex core was present, we were getting nothing. And so Mark Frederick had presented this work at Turbo Expo, and we got a really good question that was like, you just did this at 1 frequency, maybe you just chose a really good frequency. So this is why peer review and question time is good. So we went back and we did this at all the frequencies, and we chose the maximum value of this across the flow field and plotted it now as a frequency, as a function of frequency, or Struhal number, which is a non-dimensional frequency. And you can see for a whole range of frequencies, we get the same thing. So this was really cool, because this basically told us, when we hypothesized this at the end of the paper, we say, look, we have used a global instability to suppress this receptivity of the shear layer, which if we could do this in a reacting flow, this was all non-reacting, if we could do this in a reacting flow, we could break the thermoacoustic feedback loop, because now the shear layer is no longer amplifying any disturbances. We didn't take it any further, though. But somebody else did, and so Kilian Oberleitner's group at TU Munich actually showed this many years later in a reacting flow, and it's always really wonderful to see your theories being proved out by colleagues in completely different experiments. So this is a real possibility that you can sort of manipulate the stability of the flow to help suppress thermoacoustics. There was an issue, though, with how we did this. This is a sort of simplified problem. And in particular, when you have these global instabilities interacting with thermoacoustic instabilities, often the interaction is not linear, it's nonlinear. And so the last thing I want to talk about is this interaction between thermoacoustic and hydrodynamic instabilities, and particularly instabilities that are globally unstable and the potential for nonlinearity in the interaction. When you have nonlinearity in flows, it opens up a whole bunch of different options. Nonlinearity is just a wonderful field of complex results. But if you look across the literature, you can sort of find 3 different potential options for how the thermoacoustic and hydrodynamic oscillations will interact if the flow is globally unstable. The first one is the one that Ben found. So the flow response to external excitation is negligibly small, and the flow only does what's happening at the self-excited dynamics. So that's what we saw. Basically no response to really high intensity acoustic forcing, and PVC doing its own thing. You can have the unfortunate situation where maybe your acoustics or your thermoacoustic instability line up with the natural frequency of the globally unstable flow. And this was an experiment that Ben Emerson and Tim Lewin did in a wake flow. Here I'm showing a spectrum. So again, x-axis is Struhal numbers, so that's just non-dimensional frequency. I'm showing a spectrum of flame oscillation, lateral flame oscillation. In particular, the sinuous mode, which is that nice von Karman vortex shedding that we saw before. I'm going to only highlight a couple things about this paper. This is an extremely subtle study, and I would encourage you to read it if you find this interesting. But basically, without acoustic forcing, you see at the density ratio that they're running this experiment, you see this nice oscillation at the expected Struhal number of about 0.21. So then what they did was they took acoustic forcing, it was longitudinal acoustic forcing, and they swept across that frequency. And what they saw was when you forced at the natural instability frequency, you got this massive response. So really, really susceptible to forcing, huge amplification of the input, because now you're forcing something that's already self-excited. And this can cause potential issues for thermoacoustic systems if you have an acoustic mode that lines up with one of these hydrodynamic modes. The final thing is that you can have these weird nonlinear behaviors in coupling between the hydrodynamic mode and the thermoacoustic mode, and there are a few different options. So some examples that folks have found in the literature. First is a study that was done at DLR, so Adam Steinberg, Isaac Box, Michael Strohr, Cam Carter, and Wolfgang Meyer. They had a situation where instead of what happened in our experiment, where the PVC suppressed the thermoacoustics, the PVC and the thermoacoustics existed together, and they interacted. And so the thermoacoustic oscillation sort of caused this breathing in the PVC, and the PVC created this weird tilting in the flame. But these two things were happening on top of each other, and there's some really neat data analysis in the paper to kind of pick apart how these two different motions and turbulence are impacting the flame. The other thing that can happen is you can not just get dynamics at the frequency of the PVC and the frequency of the thermoacoustics, but nonlinear phenomena create all these other frequencies. They're called sum and difference frequencies or interaction frequencies. So this is work that Jonas Moek did during his PhD at École Centrale, and here he's showing oscillations due to the PVC only, but in cases where you had both the PVC and some acoustic mode, you could get these really strong interaction modes or sum and difference frequencies, which are classic examples of nonlinear behavior that showed up really strongly in the flame. The final example that I want to show is one that just got accepted to the Journal of Fluid Mechanics a couple weeks ago. This is a collaboration between my group and my soon-to-be former student, Ashwini Karmakar. She just defended her PhD 2 weeks ago. Isaac Box at DLR, and then Santosham Chandra and his grad student, Sarkta Gupta at IASC. Here we're taking data from one of Isaac's experiments. It's a dual swirl injector where we can keep the total flow rate constant but split it between an outer swirler and an inner swirler. And in true DLR fashion, there are like tons of lasers and cameras. We're measuring stereo PIV, OH pliff for the flame, and acetone pliff for the fuel. And so as we look at these different air splits, if you put 20% of the flow through the center nozzle, the remaining 80% through the outside, what you're seeing is a high-speed video. In the red is the OH pliff, in the green is the acetone pliff, and you get this massive symmetric oscillation. This is a thermoacoustic mode, we could tell again with the pressure, as a result of the oscillations, acoustic oscillations in the rig. So really strong thermoacoustics. As we add more flow to the center line, 50% of the flow through the center. Now if you watch this video, you're getting this asymmetric side-to-side motion, and this is, again, if you look at the velocity field, a result of a precessing vortex core that's excited as you put more flow through the center. And so when we looked at the relative amplitudes of these two instabilities and their frequencies, so on the x-axis of these plots is the air split, so the percent going through the middle. On the left is the frequencies. There are actually 2 thermoacoustics modes in this experiment. It's a really cool rig. There's a lot going on. But what I want to point you to are the purple dots, which is the big thermoacoustic mode, and the black stars, which is the PVC. And you can see on the right the mode amplitudes go opposite. So as the PVC grows, that thermoacoustic mode is suppressed. And it's hard from just looking at the experimental data to say anything causal, but this is why you have friends who are theoreticians. So Sartik and Santosh took this data and they did a weekly nonlinear analysis up to a 3rd order of nonlinearity, and actually could derive a term or an expression for the amplitude of the thermoacoustic mode, which is what I'm showing on the bottom. And there's a lot going on here, but I want to point out 2 pieces. One, it's dependent on the difference of the frequency between the acoustic oscillation and the hydrodynamic oscillation, so that's the omega A minus omega naught term. But more importantly, it's dependent on the beta A0, A1 term, which is the nonlinear interaction term between these 2 hydrodynamic modes. And that term is about 4 lines long, which is why I didn't put it on a slide. But if you read each of the terms in there, you can actually see the mechanism by which the PVC is suppressing the symmetric response and hence the thermoacoustics. And so now we have theory to show us why we're getting this particular response. All right. So in the last few minutes here, I just want to talk about what this means for design. Hopefully I've showed you at this point that there are lots of really interesting ways that thermoacoustics and hydrodynamic instability can interact. You have these disturbance amplifying flows that can really drive the instability. You have these globally unstable flows that can cause all these weird nonlinear behaviors. But now what do we do with all this information? Well, if we think about how we design engines, and I'm using gas turbines here as an example because that's my main home, but I think this pretty much applies across the board. Current combustor design methodology sort of has three basic steps. So you start with your current design and then you use design tools. And these design tools are empirical, curve fits, maybe 1D models, some old guy in the group who nobody let retire because he knows everything, right? So like you get a baseline design from these tools, and then you take the baseline design and you put it into CFD, and I would highly recommend folks go back to Thierry Poinceau's 2016 plenary lecture at this conference in South Korea, where he talked about how we're really improving CFD tools for capturing thermoacoustics in design. But depending on how much computing power you have, this can be RANs all the way up to LES. And then you have a part, you prototype it, and then you rig test it, and you test it and test it and test it and test it until you're pretty confident that it's going to be okay. And then you can put it in an engine for an engine test and then send it out. So where do we typically find thermoacoustic instability in this design path? Well, if you're lucky, if you're really lucky, you find it in the CFD stage. But you need to be doing some pretty high fidelity CFD, particularly capturing the acoustics, in order to do that. Again, see Thierry Poinceau's lecture for that particular issue. Where you mostly find it is in rig testing. And it's kind of a pain because you've already built a thing, you've got a rig, and now you got to go back and you got to redesign it and you got to try it again. And it gets expensive and time consuming, but at least you found it in the rig. If you're having a bad day, you find it in an engine test, right? Because now you've got this part that you've interfaced with all these other parts in the engine, and it can be really bad. If you're having an extra bad day, you find it on an engine installation, and you never caught it in test. And this happens more regularly than you think it should, because these instabilities are so geometry dependent. You know, it can depend on the fuel skid that you're using to run your engine. So the question is, how do we try to avoid this? Well, the first thing is that there are thermoacoustic instability prediction tools. And so they come in a couple different flavors. Some of them are Helmholtz solvers with flame models. We have these things called network acoustic models, and I've put some names of some folks, and I'm sure there are many others who are developing these really nice types of tools. But what I'm proposing is that we also add this hydrodynamic stability theory to this design loop, knowing that these types of thermoacoustic tools don't capture all the rich dynamics of the flow field in addition to the thermoacoustics. We need another tool. And it turns out that this stability theory is highly tractable and not all that computationally intensive. And it can allow us not only to catch these instabilities, but also potentially design in some of these tricky nonlinear interactions that would allow us to suppress thermoacoustics. So with that, I'd like to thank everybody. It's been a real pleasure to give this talk. I know we don't have question time during this session, but I will be around for the rest of the week, and I'd love to talk about this. So thank you for your attention, and have a good day.
Thank you very much for a very, very inspiring, very interesting, and very educational talk.
Thanks.
And I have the honor of passing this certificate to you.
Oh, thank you.
For giving this plenary lecture.
Thank you.
Congratulations, and thank you again.
Thanks.